So welcome to our session today, organized by the FASS Singapore Research Nexus. So thank you for coming to our session on environment, climate change and policy in Singapore and the region. So I'd like to quickly introduce what the Singapore Research Nexus is about because we've organized this event. We'd just like to tell you a little bit about what we do here. The Singapore Research Nexus was launched in 2011. It's a research initiative from the Faculty of Arts and Social Sciences at the National University of Singapore. So it's been many years in the making because our faculty's history of research dates back to 1929. So much of our researchers' arts, humanities, and social science work covers the Southeast Asian region and beyond, but there's still a huge chunk of work that focuses on Singapore itself. So we've thus created the Singapore Research Nexus to serve as a showcase for past research, for current research, and as a platform for that you can use for future research in Singapore as well. So the aim is to kind of provide a useful tool for academics, policymakers, as well as those with a general interest in how research has kind of helped shape Singapore. So we've collected thousands of academic publications. We have full text versions for browsing via the NUS Scholar Bank. And you know, there's a potential amount of resources that you have over here. We also have Singapore-related creative work as well, encompassing novels, poems, plays, short films, all written by FASS faculty and students, past, present, as well as an SG photo bank. So if you want to use pictures from there, feel free to. So the Singapore Research Nexus publishes weekly highlights of FASS research pertaining to Singapore, and we organize regular events such as these to present faculty research and publications. So this is the fourth of our policy outreach event series. So our next one, the fifth one, is scheduled for next March. Okay, so we envision the Singapore Research Nexus as a vital resource, you know, and we hope that you might find it as useful. So very quickly, I'd just like to quickly talk about some upcoming events that we have. Some of these are organized just generally by the research division. So we have a FASS Brown Bag seminar by Dr. Stephen Pan from NUS Psychology. He's talking about using AI-generated practice questions to implement pre-questioning. We also have a Brown Bag seminar coming up by Dr. Michelle Ho from CNM. And then we also have a book launch by Dr. Vinita Sinha on temple tracks, labor, piety, and railway construction in Asia. So if those are events that you're interested in, feel free to kind of go to our events page to sign up for these ones as well. So that's just the opening spiel. So I'll keep it quick so that we can kind of get to today's program. So I'd like to introduce to you our chair moderator for today's session, Dr. Susan Owen. So she is an environmental policy researcher and educator who works with physical and social science research to better understand the limitations in environmental management practice. And, you know, with the focus on climate adaptation policy in the context of environmental and human systems, she's interested in how we respond to complex and at times seemingly tractable issues faced when developing policy to support sectoral adaptation to climate change. So this seems particularly important in times like these when we accelerated climate change. So her research focus has been driven by a curiosity about mismatches between science, policy, and perception, especially when faced with questions about adaptation to slow onset environmental change. And her work has also intersected with adaptation questions across a range of sectoral areas, including flood risk, biodiversity, marine economies, and renewable energy. So if you're interested in some of these issues, you can talk to her about it. She's also held several positions of in an academic context, including graduate advising roles at the University of Auckland and at Simon Fraser University. So she's also the Associate Dean of Postgraduate at the Faculty of Science at University. I won't take up your time any longer. Feel free to take the call. Thank you so much. Thank you.
Hi, thank you, Dana, for the introduction. Excuse me. I'd like to welcome you all here to listen to some engaging and some interesting conversations about work that our researchers have been undertaking and thinking about in terms of the policy practice. So we will, I'll introduce each speaker in turn. Each speaker will have about 20 minutes, and then we'll have an opportunity for 10 minutes of conversation and discussion. So we can take questions from the floor, but also from our guests who are online as well. We'll have questions from them. So it's my pleasure to introduce our four speakers today, Assistant Professor Hao Tang, Professor Paul Kench, and Associate Professor Nikhil van Brugel, and Associate Professor Marvin Montefreo. International experts in their fields, our speakers are adept at identifying future relevant questions, examining novel issues, and translating evidence from complex environmental and social problems to inform decision-making for resilient futures. They will share insights from their research and challenge us to think about the significance of these observations for management and research. And it's my pleasure to introduce our first speaker, Assistant Professor Hao Tang from the Department of Geography at Yale-NUS. Assistant Professor Tang's work is at the forefront of remote sensing and geospatial technology, focusing on the critical task of mapping and monitoring terrestrial ecosystem dynamics in the face of climate change and land use alterations. Recent advances in geospatial technology have revolutionized our ability to monitor, analyze, and respond to environmental and climate changes. Innovations in high-resolution satellite imagery and predictive modeling have significantly improved the accuracy and efficiency of environmental assessments. These advancements inform decision-making on climate adaptation, biodiversity conservation, and environmental protection, and they support evidence-based policy frameworks to foster the important questions that sit around sustainable development and resilience against climate change. Dr. Tang's research exemplifies the transformative potential of these technologies, integrating remote sensing data, mathematical models, and ground surveys. His work characterizes the spatial temporal changes of 3D vegetation structures and their impacts on both nature and human society. So please join me in welcoming Dr. Hao Tang as he shares his expertise in his talk, Recent Advances in Geospatial Technology in Support of Effective Environmental and Climate Policy in Singapore. Thanks, Hao.
Thanks, Dr. Owen, for the introduction. It's very nice to be here with everyone and talking about one of my favorite topics and a topic that I've been working for decades on the geospatial or the remote sensing technology. I noticed that one important topic in this seminar series is policy, or in other words, the decision making. And one famous quote is always goes like this: you can't manage if you don't measure. And this is what I do. I do measurement, and you measurement at different scales such that you better support the management side. And here I'd like to share a little bit more on the recent advancement in the geospatial technology part. A little bit background about myself. I work on earth science, forestry ecology, remote sensing, LiDAR, etc., etc. So it's my ultimate goal that the three-dimensional Earth observation that will be playing a crucial role in support of natural resource management. I've been working with multiple NASA projects, including the ongoing one, for example, the H, which I will share a little bit later, but also at more detailed level in terms of ecosystem, spatial data modeling, and other climate and conservation initiatives. So let's go to the big picture first. This is the global carbon cycle diagram, which probably everybody have at least seen or heard about that. I'm not going to go to the full details of this, but just want to draw attention to one part in particular, the land component, which is some topic that I've been working for quite some time. Why is the land component interesting? Well, the most intriguing parts, well, there are actually two important parts about this. Number one is that if you look at not just the first number, but also the second amount, the uncertainty component is the largest on the land part. And number two, over the land, we actually have a two-way traffic. What I mean by that is, on one hand, we see a lot of the carbon emissions from the land, predominantly through the land use and carbon chain. But I also see that it actually become a major carbon absorber, primarily through one powerful tool that the nature has been giving us, the photosynthesis, by taking down the carbon. So by itself, it's actually a pretty powerful climate regulator. Now it comes down to the actual details about measurement, which is that what are the exact numbers and how we'll be able to come up with the numbers shown here. And this is where actually geospatial data or remote sensing data has been playing a quite important role when we do this kind of counting. How exactly we do that? Well, of course, we're not going to go from nowhere. There are specific guidelines compiled by different experts. One example of one good attempt has been this: the climate mitigation framework on REDD+. REDD+ here represented for, well, the full acronym here, the reducing emission from deforestation, degradation, and conservation of the forest carbon stocks, sustainable management, and enhancement of the forest carbon stocks. So this is the UNFCCC REDD+ scheme, for those who are not quite familiar with. This is probably one of the highest level of the policy approaches and the positive incentives with respect to the land management. But how exactly we're going to do that? How exactly going to implement that? There are some simple equations here. I'm sure that's not too difficult for people to understand. In terms of overall carbon emission, this is how boiled down to the bottom, how we be able to calculate this. What states here is that in order to account the carbon emission on the UNFCCC REDD+ scheme, we need to basically boil down to, well, a measurement of the forest area change. We also need to know the associated carbon stock change, which is called the emission factor. And also, in a best scenario, we want to know what kind of forest we are dealing with: the primary forest, modified natural forest, planted forest, etc., etc. So again, key concept here: activity data. That is basically the area of whatever you've been doing or managing, and an emission factor, change in the carbon stock per unit area. Putting them all together or aggregating them all together over an area of interest will give you the overall carbon emission, well, or under the REDD+ scheme. So this oversees entire REDD+ scheme, and you probably hear this on, for example, UN level initiative, and similarly from the private sector as well. To do that, we obviously see the value or the importance of doing counting or measures. There are three different approaches when we wanted to go a little bit deeper into the, well, counts or the numbers here. The approach number one, usually corresponding also to tier number one, lowest or so-called low-hanging fruit, is that we just count the total area for each land use. No information on conversion or whatsoever, only net change between category. Well, that's easy. A simple example will be, we have, let's say, 80% of forests in, not necessarily Singapore, but let's say in other countries, Indonesia or whatever, and 20% of non-forests, or maybe doesn't make the number right. 80% forests, 15% non-forest, and 5% farmland. That's all you need to know about from approach one. And we can go a little bit further about approach two, which is about the change or specific changes about the category. Here we talk about the management. From year 2000 to year 2020, we will expect some of the changes. So if we're only using the approach one, all you need to be able to know is actually the relative percentage. But for approach number two, you'll be able to tell, for example, how much of the forest land being converted into the non-forest land, how much of this forest land be converted in the, for example, the agricultural land. So this is where the approach two be using and actually being adopted by a lot of countries as well. But that's not enough. A lot of times, a lot of land cover or land use change really happening at the fine scale. That's where we want to track these changes within a spatial domain or within on a map, basically. And that's where the remote sensing has been playing a quite important role for approach number three or tier three criteria. So what I'm showing now is one of the classical iconic example from the sun or the use of sunlight for tracking the land cover land use change. This is not happening in Southeast Asia, but in Rondônia province of Brazil. Just reduce any possible conflict of interest if that makes anyone uncomfortable in this region. What you're seeing here is 50 kilometer by 50 kilometer size, well, a little bit bigger or very close to the entire Singapore. Throughout the years, satellite imaging being able to track the loss of the rainforest over the years. This is probably one of the best examples showing the fishbone cutting when you have the major timber company cutting to the middle of the forest and expanding diagonal or orthogonal to the main road and gradually eating up the entire forest. with the total loss of the carbon in this scenario. And that happens a lot throughout the entire world and are being captured with satellite data even in the 1960s and 80s. The similar strategy or the methodology can be applied to Singapore as well. So this is one of the projects still ongoing with the blue carbon accounting. You can imagine or put the same context apply not necessarily over like entire tropics, but just within Singapore alone. When you have satellites, that's good enough. So I'm not go through the entire procedure, but the same methodology follows the UNFCCC that I just showed in the first two slides. To do that, number one, we need to know the emission factor, which is that the amount of the carbon with individual forests or individual ecosystem stratification. These are the examples of in the blue carbon ecosystem that's within Singapore. The mangrove, seagrass, mudflat. A lot of people contribute into this domain. Professor Miguel Van Brugge will probably going to talk more details about this. Here, I'm just giving you an idea. This is generally what do we do. For example, how to set up a plot, collect all the sample data, and do the analysis in the lab. But this only gives us the emission factor, not necessarily activity data. To track activity data, it's a little bit tricky, right? You can't really just go to one place saying, I see something happening and reporting that. We really need to take a whole overview or a more integrative approach. And that's where the remote sensing comes to play. What I'm showing here are the high resolution satellites from the USGS and NASA's Landsat data. This is probably they're probably earlier satellites or area imagery than this. This is the public domain that I have direct access. 1973, a few years after the independence of Singapore. And then you see the gradual development of not necessarily the port, but other parts of Singapore, and of course, the other side of Malaysia as well. Then this is the 2009, and then 2018. So you see there's quite a dramatic change in terms of the overall land development, but also the loss of the natural parts in Singapore and across the street again. And by using this type of information, we'll then be able to track the different ecosystem types. Here, again, we'll focus just on the coastal region or blue carbon regions. And this is the coastal habitat data by stacking the different time series of satellite images altogether. And this coastal resolution satellite is corresponding to a size just a little bit smaller than half a football field, or maybe a little bit bigger than a basketball field. But when you have some of high resolution imagery, for example, this is the 7 centimeter resolution airborne imagery from Singapore Land Authority, it clearly will be able to see details that's not so clear if you take a coastal resolution one. And with the improvements of the technology, you clearly see the overall improvement of the classification and therefore the characterization of the so-called activity data. And of course, we also be able to distribute the gain and loss of the mangroves, in this case, to different courses. It's not all about the negative side. We do see, for example, positive activities, including, well, how we be able to initiate some of the restoration projects or some of the coastal belts, et cetera, et cetera. So this gives you an idea, not necessarily about things have been done to, well, have a negative impact on nature, but also positive activities being set up to restore or reduce the loss. But that's not the end of the story. By putting this all together and possibly with some of the, well, machine learning and other tricks together, we've been able to forecast what might look like or what might happen in the future according to certain or key driving factors. And with this all together, we'll be able to simulate the possibility of how the blue carbon would change on the different scenarios. And this is still some of the ongoing work. After all, what do you really want to see? Or if we have to communicate with the stakeholders, this is generally my favorite part. It's something like this, right? At the end of the day, we have a map. We show this is an area have been impacted or deforested, and some of the degradation components. But that's not enough. We will need to take the samples, or what do we call of the different the theater measurements at a distributed in a distributed manner, such that we'll be able to pull everything together and give you a good estimate of the carbon or the carbon estimation. But if you just look at the green blanket there, you don't really see much of the spatial variability, and it actually is notoriously difficult to characterize it. One important measure you track the carbon change is actually through their structure. In general knowledge or in average, we expect the primary forests have more carbon compared with the hetero younger one, and it's reflected in a vertical or three-dimensional structure. And conventional technology struggle to measure that. Applies to the imagery data I showed, it applies to the radar data and a couple of the others. So really demand a better tool for that. And also we know for those further levels of conservationists, they also realize the three-dimensional structure plays a very crucial role in terms of characterizing the habitat quality. So this is why we want to look at things not only on the 2D, but 3D. This should challenge you or go beyond the typical wisdom about a satellite imagery. Green is green is green. Here we show the improvement on quality. So again, back to the Singapore Land Authority's imagery, they have the 2014 and the 2019 10cm imagery. If I'm just showing the rectangle here, it might be a little bit struggling to see any difference or any changes have happened. But if I'm being able to overlay two LiDAR data or three-dimensional point cloud together, you clearly see that there are substantial changes. For example, I can tell that over 5 years, we're seeing a mangrove green 6.12 meters, and also subtle changes on the topography as well. By combining this information, it brings more transparent and reliable estimates rather than just showing one simple number that you not be able to trace back where it is and when was that. So this can be verified by anyone who ever have access to the data. So this is my belief that 3D remote sensing can really improve the overall MRV quality and integrity. There's other things that I've been doing. This is using a three-dimensional laser scanner into the mangrove forest. What you show here, and not something generated by ChatGPT or whatsoever. It's really just 3D, or what people call the digital twin of the forest that we visited there. And with a little bit more efforts, we'll be able to, convert it into digital asset. What I'm just showing here are from the raw points, the raw 3D point cloud, extracting individual trees, colorizing them by the individual stand. So this still needs some technical improvement, but I believe we are on the right track for that purpose. And these are all good and fancy things. The problem is we can only do at a limited area and with a lot of the costs. How about do it at a global picture? Because we really know that you may have a perfect restoration at one single dot, but you don't want that to be the representative of everything, right? I heard from the UN once, or World Bank folks, what they say is that you don't want to end up with a perfect restoration project within the storm of deforestation. To do that with your satellite, I'm already showing the satellite being able to track the broad picture, and here is what the LiDAR will be able to bring you at the global scale as well. So this is one of the satellite projects I've been working with NASA in the past decade, building a satellite or laser system on top of International Space Station, shooting the lasers, measures the vegetation in 3D, as one of the diagram example showing in the bottom left figure here. I'm not going to go into the details, just some of the quick numbers here. Selected in 2014 for $94 million, joint product usually Maryland, the NASA Goddard Space Flight Center. Prime mission ended April 2021 and extended once towards March of 2023. Hibernation for a year and then back to function again, and it will run until the end of this decade, so 2030. It's still operational, and in fact, going to have the science team meeting next week and discussing about the new release of the data sets. So what does it mean? What does this all mean, right? So this is what the current scheme that people be using in terms of red plus scheme. We try to get the activity data for its extent, loss, and again, lay out a couple of different plots there. How many plots do we have? Well, again, depending on project area or depending on the interest. Sometimes a few, sometimes 1,000 according to different observation networks. And the best effort I've seen, for example, for some of larger countries, set up the observation network, 1 million, that's the best guess. And when you have all the satellite go passing by, that you'll be able to increase more by today, more than 1 billion of the plots global wise. So it's not real to scale, actually the real bar will be even much bigger than that. However, let's not say that we do not have problem. The data quality and quantity is always a problem, and we always look very carefully into the calibration component. And it probably can see that in terms of calibration side, is still well underrepresentation in the Asia component, or in particular in the East Asia, but also in Peninsula in Indochina as well. And I'm just trying to show that when you incorporate the local data, how big the difference will be. This is some of the work that one of our PhD students at geography has been doing, trying to do a more local collaboration of the satellite data and forest inventory data. So I think you try there too in Laos. So by combining these two together, we'll be able to effectively reduce the original bias in the estimation of JEDI. And even notice that I'm going to go a little bit quick here. So after all the reconfiguration and calibration, we show that we'll be able to get rid of the bias, but also improve the overall precision of the estimation at the country level. So that shows a great promise how we'll be able to help countries to do their overall carbon accounting in the forest sector. Some of the successful stories have not necessarily happened to Laos, but other countries as well, and being used in their official report to the UN. But that's not the end of the story. Technology always evolves. What we've seen here are a narrative from, well, as early as 2003 to some of the latest technology, 2018-ish, JEDI and ICETI, our big sibling. I'm also working with a satellite mission called H. It's a new form for the multi-beam swath mapping LiDAR. It's called Earth Dynamics Geodetic Explorer. And it aims actually to address not just the forest side, but also the ice side as well. So the overall science goes trying to check two target observable terrestrial ecosystem structure as well as ice elevation. As we all know, with the climate change, the polar region actually suffers most because of the amplification effect there. With that, I stop my presentation. It's my belief that three-dimensional Earth observation is rather crucial for the overall stability and climate studies. Thank you very much.
Thank you very much, Hal, for, I guess, taking us through a journey and through some of the changes in technologies, but also the advancements and how that's allowed us to think about vertical change, but also across different scales as well. We have a few minutes to share in conversation with so if there's any questions from the floor or online, please do let me know.
Thanks, Hal. I guess a question, I mean, it's very impressive, the level of detail that we can get to. So picking out the mangrove that grew 6 meters on that line, for example. But is there a limit to the scale that's useful and then a scale that becomes spurious? And I mean, how can we can, the tendency we want to keep chasing better, higher resolution data. Where's the line where enough is enough to give us the answers that policymakers or whatever find useful? So you've got to detach yourself being the scientist from that.
Well, so you just ask probably not just $1 million question, but sometimes could be like even $1 billion question, depending on investors' perspective on that. The short answer to that is spatial resolution doesn't matter. Actually, we just had a paper published on science collective efforts from the NASA's CMS carbon monitoring system community, arguing that higher resolution does not necessarily generating high accuracy or confidence in terms of carbon accounting. What really requires is a domain expert's knowledge about at what relevant scale or resolution should we do that. Of course, the improvement of the sensor by itself can help a lot, but that domain knowledge by itself matters equally. So you will be able, or the domain knowledge, a domain expert will be able to tell us at different forests or different ecosystem, the requirements might be different, and that matters a lot. We shouldn't just go purely for the sake of the high resolution by themselves. And of course, there are natural variability associated with that. I will best address that. I don't have anything at the moment. Again, this is the open science component.
Any other questions from the floor? Question from the our online audience. Have there been any examples of JEDI being used for specific policy that has been or will be implemented?
Well, that's a good question. I would say that it has been mentioned in multiple high-level documents or policy reports about the use of the JEDI data. Then, if it is really being used in specific policy, to the best of my knowledge, still limited. One example I alluded to in my talk is that one African country is actually using JEDI data for the national greenhouse gases reporting. This is the example that I'm aware of. Maybe there are others. I see people still starting this since it's a relatively new instrument. Whether that will be actually used in a specific policy, we will leave it to time.
Getting on discussion I've had more with Hao. This is very impressive and fantastic what you can do. I love especially the lighter stuff. Of course, a lot of the spatial analysis data needs to be verified and basically fed with ground data, field data. You see the amount of the amount of dollar, let's say the funding you mentioned here with this kind of project. There are kind of a multitude of many times what you would be able to get for field work. So what kind of, if you talk about policy and you really want to get better data, both on all kind of different spatial scales, how can we avoid that this seemingly push to replace field work for remote sensing work? There's an impression you get much from the literature. A lot of the justifications I read in papers that are about remote sensing or vegetation change, etc., is to make it more efficient. The implication is always to get rid of the inefficient field work. But at the same time, all kinds of analysis show that the field work is still really lacking. And giving in terms of how accurate we can estimate from field work, let's say biomass or biodiversity, etc. But that same field work is going to use in the modeling and the verification of your remote sensing data. So I feel that if we continuously develop more better and larger and more sophisticated remote sensing approaches, we completely ignore the field part. Then there is something going to go wrong, I have the feeling. So my question basically is, I'm assuming that the remote sensing community is conscious of that because the use of field data. Is there kind of a push from that side as well to improve the quality and the quantity of field work to feed into this kind of remote sensing work?
This is a good question. It's not really easy to answer your question from an individual's perspective. It is really subjected to the the funding agency or government to look into this question. For me per se, that I usually value both the remote sensing side as well as the field sides, because that's both of them are equally important if our ultimate goal is to address climate and sustainability problems. But back to your question, remote sensing actually can do whatever that it measures. What it essentially measures are some of the physical quantities in terms of either radiance or the distance. Whatever else being so-called measured, that's a complete misuse of the measurement. And I usually refer them as estimation or estimated. And there's a huge difference when you just string out a remote sensing imagery and I call that thing is a carbon map or whatsoever. You properly establish and translate the knowledge between the field experts and the remote sensing data. I believe it's still an ongoing science practice and also science questions. How to best allocate the resource for that? Again, unfortunately, there's just no simple answer for that. What I can do is that the remote sensing community has made a good effort on making all the data for free. So this is again from my former department, which my former dean and the chair say that his most proud contribution to the entire community is that he made the entire 30-meter Landsat data for free for anyone, for everyone. That is our contribution. Whether the terrestrial ecology or the field group would be able to do the same thing, I will leave that to the community.
One more question online, and then this last question, and then we'll move on to discussion with Paul. Okay, so a question from online: which countries or regions have shown the most significant progress in terms of environmental sustainability, according to JEDI, and what lessons can other nations learn from them?
Unfortunately, I'm more like a remote sensing engineering part. I actually don't really track the individual progress of the countries. I'll be actually more than happy to know about that if you did a little bit of work on that, and I'll be more than interested and very curious to work with you to look into the details about it.
That's great. Thank you very much, Dr. Tang. And I think it's really interesting, again, these kind of connections between field-based studies, the remote sensing, but also these applications and understanding of what might be possible in decision making. So if you could join with me to thank Dr. Tang. Speaker is Professor Paul Kench from the Department of Geography at NUS. Professor Kench is a leading international expert in the physical and coastal processes, dynamics, and the management of coral reefs and reef islands. Professor Kench's research addresses the critical challenges facing coastal systems. Over the past 3 decades, he's worked at the forefront of coastal research and management, particularly in small island nations. His work encompasses field-based assessments of coastal change, the impacts of sea level rise, and the development of coastal adaptation and management solutions. Having represented small island nations at international fora, Professor Kench advocates for resilient adaptation plans that include a spectrum of options to safeguard communities over the next 30 to 50 years. In today's presentation, titled Coral Reefs of Southeast Asia Are Under Threat from Climatic Change, Professor Kench will provide an overview of why coral reefs are important for coastal communities, the threats to reef health and structure, and will introduce new research aimed at understanding existing reef growth performance and predicting future trajectories of coral growth. By examining these dynamics, Professor Kench's research offers evidence-based insights for policymakers and practitioners working to connect environmental and social systems and to plan for the protection of coastal communities in the context of rising sea levels. So please join me to welcome Professor Paul Kench as he explores advancements in research on coral reef structure and the implications for coastal communities.
Thanks very much, Sue, and good afternoon, everybody. It's my pleasure to be here. As Sue indicated, I'm an earth scientist too, but like Hal. And so my talk this afternoon is hopefully going to try and challenge some of your ideas about coral reefs and why they are indeed threatened, and maybe expose a whole lot of knowledge that we don't know about coral reefs that I believe should be very pertinent to policymakers and managers. It's widely believed that coral reefs are under threat, and in Singapore, we're sitting on the edge of the coral triangle, which generally needs little introduction to most, but in case that isn't the case. The Coral Triangle is seen as one of the world's biodiversity hotspots, particularly around the immense biodiversity treasure that's stored within its coral reef systems. It represents 100,000 square kilometres of coral reefs in this region, with something like 76% of all coral species represented in the Coral Triangle. And in total, about a third, 34% or so, of the Earth's coral reefs are in this region. And it's also a region, of course, where we have immense population pressure on our coastal and marine environment. The provision of services, these are kind of the highlights that you read as soon as you start entering the coral reef literature around the value and ecosystem services of coral reefs. They sustain the livelihoods of more than 120 million people in this region alone. They're vital for food security. Coral reef fisheries, for example, are reportedly worth something in the region of 2.4 billion annually, around the importance of coral reefs, and tourism in the region of 12 billion US per year annually. So, given the importance both globally of the Coral Triangle, but also regionally to the nations and communities of Southeast Asia, coral reefs are something we need to think very carefully about, particularly around conservation and management. I guess given the high profile and recognition of coral reefs, they've been monitored in this part of the world for some 3 decades. And there are, well-articulated coral reef monitoring networks through the region, and the coloured red dots on this panel, which have been tracking the amount of living coral on these reef systems for some 3 decades. Nicely summarised in this article by Chan in Communications Biology, which, given variability through time, the comment is it's some remarkable stability in the proportion of live coral over the past 3 decades, at least at sites that have been monitored. Okay, and I think that's an important point. There's so much population pressure, physical destruction going on in our reef systems that aren't actually located in the monitoring sites. I'm going to kind of start broadening your thinking about coral reefs. And so here's a nice example of a complete reef system. The focus traditionally around examining coral reefs is what I call the living coral veneer. And if we put on our snorkel and mask and go snorkeling off the edge of this reef, we would hopefully see this nice flourishing coral surface. I'm not a coral reef biologist, I should add. I'm an earth scientist. What excites me more is this bit. Okay, if I stick my head out of the water, what I like to look at is these vast 3-dimensional structures, both that run, I guess, landward of the reef crest here, and both vertically through the reef structure. These structures are essentially composed of the incremental balance of construction processes of corals and other organisms that are secreting calcium carbonate in their skeletons and are slowly accumulating through time, versus the destruction processes of bioerosion and storms that are breaking up corals and leaving all that detrital material in a heap, if you like, on the reef matrix. And it's the balance of those processes over several thousands of years, controlled by sea level, that develops these 3-dimensional structures that you see. How do we know what the reef fabric is made of? Well, if we go along with our rotary drill rigs and drill holes through these reefs, we come up with these, or we extract these kinds of cores which show lumps of coral, lumps of gravel and rubble that are kind of all packed in to this reef sequence. So reefs aren't just the living veneer of coral, it's also this 3-dimensional structure that has evolved over thousands of years in response to sea level fluctuations, which have been marked in this region. So thinking about reefs then, not just as ecological veneers, but also as geomorphic structures, we can then start to think about what are the eco-geomorphic services that are afforded to communities and countries associated with the existence of coral reefs. So here's 3 of the major ones that have been discussed. The first, of course, the reef structure provides the foundation for the living veneer of the coral. And I want to point out one difference. Much of what we hear about coral reefs is from this what's called the fore reef slope, the bit that's draining off under the water here, where much of our monitoring effort takes place. Equally important to the structure of the reef is the ecological veneer on what's called the reef flat. This is an example over here, which is still highly productive and calcifying and adding to the reef structure. So it provides a platform for this, for the ecology. It also, in many places, provides the physical foundation for communities to live on. The sediments and calcium carbonate products generated on reefs are often swept by waves and currents to form islands or form the coastal margin, which are occupied by coastal communities, all as a consequence of the dynamics of reef systems. And the third point, which has started to receive a lot more press, is the role of coral reefs acting as, let's call it, coastal protection mechanisms. And I'll explore this a little bit further in this slide here. This is just an oblique aerial shot of an island, but you can clearly see the edge of the reef running around here, reef crest. And you can see these oceanic waves that are traveling towards this reef crest. You have reef slopes in the order of greater than 45-degree angles, so very steep, deep ocean systems, waves propagating across this reef surface. They start to interact with the coral reef shoal, break and release their energy. And we've done multiple experiments deploying wave gauges across these systems to look at how much energy gets extracted out of this wave transmission process. And what we've discovered is that up to 90% of incident wave energy can be absorbed by the presence of the reef structure. Of course, a number of commentators have picked up on this and come out with these kinds of numbers. And this one here, 1 kilometre of healthy reef saves greater than $1 million in coastal protection every decade in Southeast Asia. Really don't know how they come up with those numbers. Here's the other study, relatively high profile one in Nature Communications a few years ago, that was trying to look at the flood protection value because of the presence of the reef structure. Exactly in where we are in this part of the world, it's estimated it's over $50 million annually in coastal protection afforded to coastal communities because of the presence of coral reefs. All right. So given that the reef structure itself also has some pretty immense value to the region and to countries and to communities, it's then worth reconsidering what the threats are to these coral reefs and how does that propagate through to these ecosystem services that we've just identified. Are coral reefs under threat in Asia? Well, I guess the answer to that is, if you ask anybody, is yes. You know, one of the biggest pressures in this region, of course, are anthropogenic pressures, but I'm not going to spend a lot of time talking about that this afternoon. But things like blast fishing, physical destruction, construction, all have immediate impacts on the physical structure of coral reefs, let alone the biological or ecological veneer of the coral reef. But then there are these climate change factors, and given we're a climate change session, I thought I should focus on those. So what are the climate change threats to the coral reefs of Southeast Asia? Well, there's kind of three main ones that typically are discussed. The first is the increasing occurrence of marine heat waves. So here's the NOAA forecast for Coral Reef Watch, looking at the probability of coral bleaching in this part of the world over the next 4 months, and it's high. This dark area here is alert level 2, which is the most extreme alert level. Around Singapore, we're up into alert level 1 and warning grades for the next few months for another bleaching event. Last year, there was a mild bleaching event around Singapore, reporting something like 40% of the corals were under stress or threat during that particular event. The issue here is that marine heat waves are becoming more frequent and more intense, and that certainly stresses corals. It can kill corals in global bleaching episodes. And then the time frame for recovery is getting shorter between heat waves and therefore is deleterious for coral health. Another we hear a lot about is ocean acidification. And without spending a whole 20 minutes on ocean acidification, the net threat of ocean acidification is it compromises the ability of corals to lay down calcium carbonate. So it impedes calcification of the coral structure, and it can also directly dissolve, if you will, sediments and limestone materials that are contained within the reef structure. So marine heat waves and ocean acidification are two key parameters that we need to be concerned about as we look to the future and the health of coral reef systems. The third that I want to just raise is sea level rise, no pun intended. This plot here is the 25-year record of sea level rise from satellite altimetry data for this part of the world, showing that we have some, just off the coast of Papua New Guinea, some extreme rates in excess of 6 millimetres per year over the last 25 years. And if we cast your eye to the right-hand side, this is an ensemble of the tide gauge records for Tanjong Pagar, spliced together with the sea level rise projections to 2150. So for the past 30 years, approximately, sea level on the coast of Singapore has been rising at about 4.6 millimetres per year. Into the future, with the upper level storylines of IPCC storylines, we're looking at a sea level increase to around 2.8 millimetres per year over the next century or more. So, getting up there, it's getting quite high, particularly compared to past rates of known sea level change. Okay, so we're getting hotter in the sea. We've got pH issues in the sea, and the sea level is rising. What things, how's that going to play out in terms of the health to coral reef systems? Well, the three main things that we're concerned about is a degradation of reef health. The corals simply can't survive. Multiple stress events. We have changes in ecological composition because of the different resilience of different coral species. Ultimately, what we're concerned about from reef structure is the potential for reduced reef growth capacity. So both of those things lead to, and this is an oft-used diagram from a paper from Terry Hughes that looks at as reefs degrade, they start to reduce their structural complexity from sort of healthy corals to rather degraded looking corals to flat rubble sheets. Where a lot of the structural complexity is reduced, and we're left with these rubble flats, which are, as Hazel Oakley knows, are a pain to rehabilitate. Then we can then look at a compound effect of these two things when we start adding sea level rise to the problem, and that problem is reefs are likely to become relatively deeper or submerged, but also they're going to start to lose their reef structure. The rugosity or the structural complexity of corals on the reef surface, but through reducing that complexity, dissolution, also removal of the reef structure. And there are some concerns in terms of our ecosystem services afforded by the structure of reefs. One of the things we talked about was the coastal protection afforded by reef systems. This is going to diminish. What does that mean for coastal communities? Increased frequency of flooding, and severity of flooding, and impacts on communities and infrastructure, and also shoreline instability and erosion. We're also likely to come into a situation where on reef platforms that are supporting islands and communities, high instability of those islands are potentially, we hear a lot about, the complete loss of islands on reef surfaces. Last one here is something that few people ever think about. And what you see in this little animation here are the islands and reef structures of the southern islands off the coast of Singapore. And this is a PhD student that I'm co-advising at NTU, Yoshi, who set up this hydrodynamic model around the question of if reef structure changes, what happens to nearshore circulation and nearshore sedimentation patterns. So this is done to look at sedimentation today around these reef systems. But imagine if they'd gone. Imagine if the reef structure has totally collapsed. We start to fundamentally alter nearshore circulation regimes and sedimentation patterns along the coast of Singapore and indeed other areas. So there's from a management and looking from a future perspective, there's some key questions that we need to be asking ourselves and managers should be reflecting on. Will coral reefs in this region be able to grow to keep pace with sea level change? Because if they can't, we're starting to lose ground against the geomorphic services that these reefs are affording communities and nations. Subsidiary question, well, what is the current rate of reef growth in Singapore and in other parts of the Southeast Asian region? And I'm just going to move on to start to pick at that question. So how might we start to evaluate whether reefs have the ability to keep pace and grow with sea level change? Well, one piece of information you might like to know is, well, how fast are they growing? And what sources of data do we have to address that? Remember, I showed you a picture of a drill core through a reef. And if we actually radiocarbon dated that core, we can start to build up a picture of rates of reef accretion through time. Coincidentally, last year, there was an effort to synthesize all coral reef cores from across the globe to look at differences in reef growth accumulation over the past 10,000 years. Now, this is slightly complex. There's about 1,066 drill cores from the globes of the world's coral reefs. These colours denote different regions of the world: Australia, Caribbean, Indian Ocean, Pacific Ocean, Southwest Atlantic. These kind of violin plots are simply the age distribution of corals within those regions. And the bottom plot here shows changes in reef accretion rate from about 12,000 years ago to the present. The key number here really is over the past 10,000 years, coral reefs have been able to grow vertically at about 3.5 on average to up to 9.5 millimetres per year, which is quite fast. It's quite high. Interestingly, given the Coral Triangle has 34% of the world's coral reefs, there's almost no cores from this part of the world. So our fundamental knowledge of reef growth rates in Southeast Asia is largely zero, except for one very interesting study. So this is a bit of a treasure. A PhD student at Yale-NUS, Samuel Chan, did his PhD looking at the ecology and geological formation of reef platforms in Singapore. And what I'm showing you here is just a small piece of his data. This is Pulau Semakau showing a reef shoal just offshore by the channel. And these two circles here denote two percussion or core holes that were extracted through this reef surface. And they're shown on this side of the chart. You'll note a couple of things. These red dots are radiocarbon ages year before present of the accumulation of this reef. Thank you. And you'll show that it accreted very quickly between 7,800 to 7,000 years ago at about 3.5 millimetres per year. And this other core accreted about 2.75 millimetres per year. But note, it stopped growing about 4,000 years ago. And so I guess the question is, what's happened in the last 4,000 years? And the other question is, how do these historic rates of reef growth, how do they map on to future rates of sea level change? So these rates, 3.4 and 2.75, sit well below the current rate of sea level rise of 4.6 millimetres and much further behind the projected rate of sea level change in this part of the world over the next 100 years. Just a couple more slides. You've got to ask yourself, how useful is understanding how the reefs accreted 4,000 years ago to me today? I'm thinking about a reef's growing, what's going to happen to geomorphic structure? Well, the answer is probably very little, but it's the only data we've got. Why? Because the environmental boundary controls on reefs today is very much different than it was 4,000 years ago. Pollution, fishing, increased sedimentation, all those kinds of things are stressing reefs in different ways. I guess the second to last point is there are actually, other than one, no robust measurements of contemporary reef growth in Southeast Asia at all. So we don't know how fast coral reefs are currently accreting in this region. That's a problem. I could go on and talk to you about ways around that, but I won't. We've been working in a pilot site to come up with a new method or new tool to allow us to actually measure and monitor rates of reef accretion across the outer reef crest and across a reef slope using a reasonably simple device used in tight calibration. And what are these? These are little transects that we go and survey each year to basically millimetre precision that allows us to look at rates of reef accretion between years. And we're hoping with this new tool to broaden this out. So I'll make a couple of final statements. Assessments of future coral reef growth trajectories and impacts on ecosystem services, I believe, is currently constrained by a lack of rigorous data on reef growth and reef growth performance in this region. How do we overcome that? Just like Hal said, we need data. We need to expand coral reef monitoring to reef platform surfaces, not just the core reef slopes. I think we need to establish a network of sites to actually quantify modern rates of reef accretion and vertical growth. And we need to start monitoring and looking at reef topographic change so we can actually quantify how these reefs are changing over the coming decades, and we can reevaluate the economic threats that exist for coastal communities. And with that, I thank you for your time.
Thank you very much, Paul, for, I guess, sharing your work and your insights and highlighting, I guess, the structural role that reefs play beyond perhaps some of the services that we're more familiar with in terms of biodiversity. We've got about 5 minutes or so, I think, for any questions from the floor or from online, and also opportunity to chat with the speakers later. Any questions?
Quick question.
Sorry, Mark.
Yeah. Hi, Paul. Thank you for this informative talk. I know that there's a group at DBS that works at coral restoration, right? Coral reef restoration. So I wonder what sort of data that can we derive from that would help us understand reef accretion? This is coming from a non-scientist, perspective. But is there like important data that we get from coral reef restoration that might be useful for us to understand reef accretion?
And that's a very good question. And I guess that from my perspective, from the earth science perspective, those that work in coral reef restoration have my full admiration because restoring coral reefs is a high priority. And I guess it's what's the purpose of the restoration project? A lot of restoration is around securing biodiversity, very admirable goal which must be pursued. We don't want to lose these things from the marine system. The question I have around restoration is how you set your objective very much dictates how you go about your restoration. So from my perspective, restoration should think about securing reef structure, whereas some restoration programs are focused on the animal or the coral and ensuring that we don't lose corals. So there needs to be perhaps a tighter connection between those two things. But what do we get from coral restoration data that could be useful? Well, we certainly get growth rates of individual corals. But there's also a mismatch between how a coral grows and how the whole reef grows as an accumulated mass of calcium carbonate. So that that is becoming recognised. Generally, reef structures grow at a order of magnitude less than individual corals can actually grow, because you need to grow the coral and in many cases break it down and add it to the framework of the coral structure, new coral on top of that. So it's you know, I guess it's exploring ways that restoration can inform accretion better than we're currently doing. But also, in my view, we should be thinking about the restoration programs restoring structure. We went to a workshop in Bali almost 2 years ago now, or 18 months ago, where a lot of people were sharing their experience, because this is, a lot of people are doing this regionally and around the world, about best ways to restore coral. And so you may have seen them, they have these frames, Mars frames and metal structures, those kinds of things, all great. And they were trying to confront two issues. One is stabilising rubble. So these are sites where the coral's been decimated, and it's just rubble sheets, very hard to stabilise. And so they built these frames perched, you know, this far above the structure of the reef. And the question was, well, that's not reef structure, because you've got this living coral, then you've got this half-metre gap until you get to the old coral surface. So at some point, you know, that restoration needs to meet structure, and you actually build the reef as well. There's reasons why they do that, of course, because all the rubble rolling around doesn't help the coral. So it comes down to that, what's your specific purpose of your restoration? Kind of important.
We have time for one more question. Got a couple of questions here. So yeah, just one more, I think, at the moment. I saw.
After raise hand.
Fight over it.
Yeah.
I was just wondering what you thought or what you think is the main or has been the main obstacle for research being done in this area in the Coral Triangle versus everywhere else? Is it like financial? Is it access? Is it bureaucracy? Like what, or combination of everything? Sure, but why the
start? Is it the expertise? How many reef geologists are there in that part of the world? I guess the spotlight has been on reef ecology for a lot longer, but there are also constraints around limits, permission to drill reefs, core reefs. So we have just secured a permit to drill the reefs of the Spumondei archipelago. It's taken, hopefully, it's taken a very long time, but you know, some of that, and then it's logistics like this. So expertise coupled with the right methodologies, and then certainly sorely needed, because, as I said, for a region that is so intensely important for coral reef knowledge, we know virtually nothing about the last 10,000 year reef development in the part of the world.
Just, we've got a couple of questions online, and I might ask you to take an opportunity to perhaps respond to those directly online. But just a question about, will the coral growth rate in the Coral Triangle of Southeast Asia be lower than that of coral reefs in other parts of the world? We're just talking about data at the moment.
Will it?
Yeah.
What do you mean now?
Well, I guess now and into the future. The second part is, will it be influenced by the greater stability of the triangle, and will future climate change affect the stability of coral reefs by influencing ocean currents?
Well, I guess there's, well, in my view, where you have reef systems, we have a much greater diversity of corals, and the resilience of that system has greater potential than other areas. So other reef regions have much more corporate coral diversity, really relying on a few key species. So where you have greater diversity, I think you have greater opportunity for adaptation and resilience of coral communities. In terms of the growth rates, that's very much species dependent and will vary regionally. I mean, ironically, some corals slightly increased temperatures better for coral calcification performance than for some others. So it's a bit of a horses for courses. The one was about reef structure and currents. Reef structure and the configuration of reefs is a very under-considered, very important control on currents, nearshore circulation, and nearshore ocean productivity.
And just lastly, there's one question that you may not feel, I'll leave it to you to respond to. Can artificial lab-grown coral be tuned to sort of withstand harsher environments to be introduced to address the concern of diminishing natural coral reefs?
That's getting a bit outside my wheelhouse. There's a lot of work going on looking at how we might manipulate corals to withstand climatic zones. So, for example, the researchers who are working in the Red Sea, which is sort of hotter, and other areas where are more saline, are looking at what can you learn from those corals in other regions, but I can't give a definitive answer.
Thank you. Thank you very much. Now we'll draw the questions on this part to a close, but I know that there's a couple of people in the audience with questions, and I'm sure you're happy to speak with them at the end. So if you could join with me in thanking. So it is my pleasure to introduce today's third speaker, Associate Professor Michiel van Breugel from the Department of Geography. Associate Professor van Breugel is an expert in tropical forest ecology and restoration with extensive research experience in forest recovery, biodiversity and ecosystem services in human-modified tropical landscapes. The growing interest in mangrove restoration in Southeast Asia's diverse systems is driven by the urgent need to conserve biodiversity and enhance ecosystem services such as carbon storages, as we heard from Dr. Tang earlier on, fisheries nurseries and coastal defence. Despite the promotion of restoration efforts, a lack of data regarding species-specific responses to local environments constrains success. And data seems to be kind of lack of field data seems to be a running theme here. Associate Professor van Breugel's research conducts long-term, large-scale field studies on forest restoration methods, including natural regeneration, assisted regeneration, and active reforestation to address these challenges. In Singapore, he's leading pioneering research on mangrove community dynamics, species distribution, and blue carbon across multiple scales. In today's presentation titled Examining the Environmental Drivers of Mangrove Species Distribution at Local and Landscape Scales, Associate Professor van Breugel will share insights from his ongoing studies at Pulau Ubin, focusing on the local distribution patterns of mangrove species along the inundation gradient. He will outline the importance of developing a framework of mangrove-specific and species-centric census protocols to improve restoration. Please join me in welcoming.
Thank you. Well, I tend to always run out of time, and then that means that I have to skip the most important part, which is thanking all the people that have done the actual work. And I want to do that now, so that's that members and a lot of students. So the work I'm going to talk about has been financed by MOE, Yale-NUS, and Parks provide support. And it has been based on a lot of intensive student work. So that's important to emphasize, I think. So mangroves, why mangroves? It's a bit along the same line as Paul already was telling about. They're really important with regard to ecosystem services. Their biodiversity, its coastal protection, the nursery for fish, so fishery is very important, ecotourism, etc. So, and it's one of the most effective ecosystems, or so we're being told, for carbon storage as well. At the same time, they're very heavily threatened. All the mangroves across the world is either already converted to other things like agriculture ponds or degraded for firewood collection, etc. And also by other activities, land reclamation here in Singapore. So restoration, there are all kinds of restoration initiatives going on, but they're not always as successful as one would hope. And I'm going to talk a little bit about that, but partly that's has in part to do with a similar case what Paul was making. There's really a lack of data with regard to mangroves. So this is on the top you see a map of some distribution of diversity, and as much as this is the triangle of coral diversity, I don't know if this is a triangle for mangrove diversity, but it certainly is at least some very important region for mangroves. It's by far more diverse than any other part of the topics of the mangrove distribution range. But at the same time, and this is on the lower part, a study by Sangam, a student who did for his capstone work. He reviewed literature to see where and what kind of mangrove research is being done. Well, one part of what he found is if you look at the diversity, you look at the number of studies in the studies sample he took, and you see that, well, this is the area with most diversity. There's clearly an absence of a number of studies, and is indicated here by the gray shading. You see here as well, where you do actually find most mangrove, which is called literature, is over here, more to the south and the north, of course. So where diversity, the extent and the diversity of mangroves is definitely much lower. So same as in corals, where we do have higher diversity, we have the most extensive mangrove areas, and they are probably most important for local people more than anywhere else. We have the least amount of research. So one other thing, by the way, most research that is being done is actually really focused on 1-2 species. There's very, very little research on multiple species, if you look at, or at least the mangrove community. So mangrove community ecology is relatively understudied, I would argue. So here you have another map with for Sue et al., which was Dan Vries was at our department previously involved. And it looked at studies on ecological outcome. They also looked at economic outcome, but here is the ecological outcome of mangrove restoration. There's a whole wide range of type of studies. And one thing which is, of course, calls attention is that by far the most mangroves restoration projects were focused on 1 single species, rather than 2 or more. And the majority of that focused on more than 1, there were 2 or 3 species. Which is obviously specifically a problem, again, in this area where an average mangrove area would have at least 10 species or more. So it's very focused on 2 species only. It's also because most of the mangrove restoration is still focused on this kind of approach, just planting mangroves. And it's basically, why do mangrove restoration projects often fail? Because in a certain sense, it's simple. They're planting the wrong species of mangrove at the wrong place. And mostly they're planted way too deep, in too deep water, or in places where you have too much wave energy, etc. So places where mangroves are not actually really doing well. Why at the deeper side? My personal sense, because it's the part where fewer people have kind of interest, not? So where are we going to plant? Well, put it there deeper in the water where no one really has an interest. It's common in all kind of ecological restoration. And kind of restoration approach gaining more attention and more focus is this, well, we could call it assisted natural regeneration or ecological restoration of mangroves, which is not about planting mangroves, which is creating the conditions or recreating the conditions that are more favorable for mangrove regeneration, for the arrival of seed, of propagules rather, establishment and survival of those propagules. There is an example, an image from a project in Madagascar where they're then digging channels. So water can come in again in that system. That was kind of, so that's one approach. So that's actually something they're going to try in out in Sungay in Pulau Bun, and March was starting around this time. They're finally starting an ecological restoration project in 2 or 3 on the southern part of Pulau Bun, 2 or 3 aquaculture ponds abandoned. You see them here as they are now. The idea is to fill them up in a gradient from higher to lower with 2 different soil mixtures, etc. And then basically let it go. So and then see what kind of established. The whole hope is that propagules will be coming in. Now it's too deep for mangroves. The propagules will begin establish and form new mangrove communities. This is a kind of diagram which are very common in mangrove research, ecological research, kind of diagram of the distribution of species. And this, this is also the most common way of studying that. It's not really quantitative. It's there's just recently a study published on a mangrove distribution along the elevation gradient. You see here from the higher to the lower part, and there are a few, about 150 of them, and all of them are drawings. Basically, they're not really kind of spreadsheet type of There's some expectations of what kind of mangrove species I will find there. So fewer species on the deeper side and a higher diversity of mangrove species on the inside. That's kind of expectation. So to inform conservation and specifically restoration efforts such as this one, we really need data-driven studies on the variation in mangroves, community structure and species distributions. And that not only local, but at landscape scale as well. Because as I said, actually very few studies that provide data to really confirm this kind of expected pattern. And for me, there are two reasons for this. If we are restoring mangroves, we should actually have a kind of reference point. So what are we restoring? And there's incredibly little data about that in most places across the distribution, at least in Southeast Asia, about what exactly we are restoring. Not only local scale, but also how it varies. It's the whole complexity of mangroves across a landscape. And of course, if you want to do some active management, you really have to know what are the conditions necessary for mangroves, which mangroves can grow where, etc. So I will just present this study. We going on a few years now on Pulau Ubin. It's mostly with students and a few lab members who've done all the work. And the main questions we have been focusing on is how species in Pulau Ubin are distributed along the elevation gradient from deeper at the lower tide to the higher part of their distribution. So how predictable is this distribution along the elevation gradient across Pulau Ubin, across the landscape, and what drives these patterns and this variation? What kind of ecological and environmental variables? Again, why these questions? Again, well, first of all, these are drawings. So this is a study that actually on different parts in the study make different kind of diagrams of the distribution of mangroves and what their message was partly is what actually differs across the landscape. You can't have just one study and assume that it will be all over the place like that. It differed. So yes, why this question? Well, we do know that there is a specific distribution of mangroves, or we think we know. It's a kind of classic study of ecological niches, of resource partitioning, etc. But there are actually really few studies that have done this, that have studied this in real situations. And specifically, very few studies that have done it in the diverse mangroves, where you do have this whole diversity. So second, species zonation patterns vary across regions and landscape probably. So we will really need local studies. And we certainly need longitudinal and experimental studies to better understand what drives these kind of patterns. So what we did, in Pulau Ubin, we had a couple of sites. You see the white circles, and each site we established transects along which we measured in 4-meter wide transect all mangroves of 1.5 meter and higher. We measured them diameter, height of the small ones, identified them to species, and measured the instantaneous water depth, which we, the use of tide tables and depth sensor, we converted into the percentage of time that each individual tree was being inundated. On top of that, we did it also a lot of random points across the same sites to have a background distribution. We did this in natural topography kind of stuff. Ken knows more about it probably with Paul. And we did it in aquaculture pond, the green circles, to compare. On top of that, with the blue carbon SG project, which is currently with how we are now also focusing on blue carbon stocks and fluxes, but I won't be talking about that today. So one first result of what we found is that these represent all these different transects from the inside of mangrove towards the outward edge. If it would be according to the textbook, you get this kind of nicer gradient. And what we found in reality, not quite, not at every distance along this transect, you find quite a lot of variation in time of inundation. That's because you have a very heterogeneous kind of microtopography within these mangroves, which already makes this whole concept. And a lot of studies, they study it in plots. And we kind of define zonations, establish plots. Well, this shows that there's always some questions about that approach, because if within plots, your variation might be just as high as it might be among plots. Just using normal inventory methods you would use in terrestrial forest, I think we need to rethink how we do that and more adapt them to more specifically mangrove ecosystems. This was fieldwork done, led by Jared Moore, who now works in Indonesia also on restoration projects, much bigger than we can ever study. And with Kia Eng and others who have been doing this work. Also what we found, so each line here is the distribution of elevation or inundation time, a percentage on the x-axis. Each line is a plot which shows you there's also a lot of variation among plots across Pulau Ubin in the distribution of the elevations. But again, with inside variation is almost as large or is actually larger than the across-site variation in elevation. What we found were 16 species in total, quite impressive for such a small sample area, I would say. It varies the diversity per site. Bruguera cylindrica, the dominant species, specifically more on the inside part of mangroves. Isophora apiculata, by far the most abundant species along the remainder of the elevation gradient. And the height of the line gives the probability of a species to occur at that particular part along this inundation gradient. So what we find as well, so these are is an NMDS and multivariate analysis. What it basically does, for those who do not know how to read these, it's basically the closer 2 points are to each other, the more similar they are in species composition. So these two plots are more similar to each other than they are to either one of these. These two are more similar, etc. And there's a quite large dissimilarity. That's a kind of diagram. You see if each color here, each box is a species. This will be the species composition of 4. This of 10, kind of overlap in the species and abundance of species. It's quite different from the other 2 plots. And these two are quite similar in the species and their relative abundances. So what you do see, there's a kind of gradient here. The medium elevation of all trees in the plots. I think that if you look at, you see that the plots that are growing at lower elevations are more similar to each other than the plots that are growing at higher elevations. And remember, that's despite the fact that each single plot covers basically the whole elevation gradient within the plot. It's just a little bit more, a little bit less on either side. And you can use the same analysis to look at distribution of species along this elevation gradient. So you see, again, it's kind of suggestion of a gradient along the elevation gradient or the inundation time gradient of species on either side. So at the landscape scale, there is some kind of species gradient. So we did some, what we have here is of the species for which you had enough data. We modeled basically the frequency distribution of where they were occurring along the elevation gradient or the inundation time gradient here. The gray part is in each graph the same. That's basically the random distribution of elevations or across the whole landscape, across all 13 plots. And this is then the distribution of each species also across all plots. The Bruguera here, cylindrica, appears, if you saw it was the one more on the inside, tends to grow more on the part of the gradient with little inundation time. And here we have Avicennia, which grows much more on the outside. You tend to grow more. So through some kind of subsampling kind of analysis, we can estimate the median elevation at which these species occur. Actually use this data, do some modeling stuff. And what you see is this kind of gradient of species occurring. But what you also see is those species are basically all overlapping in there where they are able to grow, at least as larger individuals. And you see here a smaller group of species that are more on the outside and a larger group inside, what you would kind of expect. Again, yes, so there is a kind of pattern, but it is very variable across the landscape. And if you look at individual plots, you don't see this order of species occurring where they're most dominant. Each plot has its own across the island. So it's very, very variable. Well, it can be, and the question here is now, is this ecological driven, or is it kind of more stochasticity, so random process of dispersal, etc., or is this a consequence of Pulau Ubin being very heavily disturbed? And if you would let it grow for much longer, you would have more predictable patterns. Well, our plan is now to try to repeat this study. I'm writing a proposal to get this done across multiple sites across Indonesia to see to what extent this kind of patterns are repeatable. And again, both on local scale, to the landscape scale, and then how landscape scale patterns are going to be repeated or not across the larger region. and what bigger environmental gradients such as salinity, for example, or geomorphology or whatever biogeography kind of explains those kind of differences. What we also did was a comparison here. Remember, we did 13 sites which some kind of natural topography. It wasn't majorly altered. And we also had 5 sites with along the dikes of agricultural ponds. Just to see if the distribution of species along the elevation gradient was similar. It was, I would say, fairly similar. What you see here, the brown one is on the dikes around those agriculture points, and the green lines represent the distribution, more natural topography. And the green and the brown shaded area represent the random points in both environments. So this is the same distribution we saw earlier, and as you can see, the dikes represent a wider distribution of species. Fairly similar. So in a certain sense, there's quite a good regeneration going on those dikes. Surprisingly, we didn't expect it. All the number of species is comparable. Well, some last small study we did with Taylor Slowey worked with us. She's now an assistant prof in Old Dominion University. She took the initiative of the seedling study when she worked with us, and you see here people doing an amazing amount of work. There are a lot of seedlings out there, a lot of work. As you can see, it's fun. You get sometimes basically waist deep in the mud. That's questions to what extent we're actually affecting our own study system, but that's always difficult. So basically what we did, we tagged many thousand seedlings, and we followed their fate for 1.5 years. And one time we retagged newly recruited seedlings across 4 different sites. So if you want to understand seedling dynamics, there are all kinds of different reasons why seedlings or propagules are where they are. It's about, let's say, propagule dispersal. So the whole dispersal, how far they're dispersed, how many of those propagules are being produced in the surrounding, etc. How well they're kind of stranding along this gradient. Then, of course, establishment and survival. Yeah, not all, almost. So what we looked at is at survival, mostly seedlings, establishment and survival, and we looked at 2 different variables. One is the inundation stress, and one was something that doesn't really receive much attention in mangrove ecology, which is shading stress, so light, because mangroves eventually are also just plants, and plants need light. Now was the Straits Times published an article on this paper, and the title was a bit unfortunate. I found something along the line of that we discovered that plants need light or something like that, which is not quite the message I hoped for. But what we did find is that light was actually, first of all, here you see the time flooded. So there's one very environmental gradient, and then the amount of light available. And you see it's not very simple, it's a very complex gradient with all kinds of different combinations. And we used that to try to model survival as a function of both light availability and of inundation time. And what we found here, in most cases, light was a better predictor than inundation time. Inundation time not quite, which I think is mostly actually a factor of our samples. Although we tagged thousands of seedlings, we probably should have tagged tens of thousands of seedlings, etc., and followed them for many years. And hopefully we'll be able to do that. Well, one last one. We're now following up with Nikita over there as her work. We'll be focusing on plant trait variation, and to what extent can we understand distribution of different species along that gradient when we take a good deep look at what are their characteristics in terms of leaves, of roots, of vessel diameter distribution in their stems, and all kinds of other things. Because the idea is that basically the distribution of species is really an interaction between the particular traits of a species and environmental conditions, and together kind of they drive where you would be expecting them to grow. And here with 2 students, Jiamin and with Charmaine, they already did studies, some trait pilot studies, and they already found some wood density, hydraulic conductivity, driving a difference in where seedlings were growing, and then further moderated by the specific leaf area. But this is really focused on water use, and specific leaf area has a lot to do with light. So this kind of first step was kind of a promising start for this kind of studies. Okay, I think that's it. Just within minutes.
Yes, few minutes.
What sort of gradients are you talking about? That gradient a fair amount, but where we talk vintage slope is what?
Yeah, so literally the relative height. So how long, and well, the most important thing is how long this surface is being inundated. Really from the deep end of the mangrove distribution along the gradient to the high end. But it's not one single, it's not spatial single gradient on it really.
Yeah, well, that's way,
Really the gradient of being inundated. So the gradient for mangroves on our side varies somewhere between 60% of the time inundated, like most extends, to 0% on the high end. That's basically where we found mangroves.
in general, what's your fall between seaward side and your landward? Half a metre max is an elevation difference between those two.
Depends a lot because you have some parts which are very, very well. At some Boulevard, everything is very small scale.
Yeah.
And it's mostly goes kind of, you have, if you look at distribution, it's mostly, it goes like you have a bit of, well, you can see it actually here. So you have most of the mangrove distributions, it sits somewhere in the middle, most of the land, basically. Mangrove sits in the middle, and you have much less on the outside and certainly on the inside. So it's basically integrated goes like this. But it differs a lot. So we talk about island and fringe mangrove, so it's very short gradients. Very different from what you would see in the Sudan, probably on Papua, which is very long gradients. But even in those very long gradients, it also goes with tidal creeks, etc. That's a bit what I say from a lot of the protocols for mangrove inventory, they really look like they're taken from terrestrial forest and forestry kind of literature. And what we are learning now is that you just can't really use that approach in mangrove research. It's too fragmented. There's too much variation with insight. So my argument is we need really focus on individual tree level measurements rather than plot level or very small plots. Otherwise, you're getting too much variation within your site relative to the complete variation across sites.
It'll be interesting to look at three-dimensional topographic complexity. That information across it.
That's right. Proposal. Let's do that. So
3D.
with how
Sounds like
it's
a
low enough into the
Nexus
lighter.
scanner.
Yes, I see the three things here combined.
It's the
Three-dimensional structure from corals and then mangroves and seagrass, probably not very complex.
Seagrass. It sounds like a dinner conversation.
I have a
Thank you.
question, something related to what you just mentioned. So these are all based on inundation periods, right? Nothing got to do with elevation. But is it possible for you to have a model with elevation at all? Because I'm interested in that because I'm looking at pollen in the sediment course in the mangrove itself. And I do see the change as you go down the sediment course in terms of vegetation presence. And this could be just 50 centimeter core, maybe up to like the last 100, 200 years. And if I can relate it to elevation, then this data is really useful for me. But I'm guessing this is more for inundation period.
Well, what we did is we measured literally in the field. We also had to do our field work when there was water. So we measured water depth on a minute. We have depth sensors that log the water depth. And then we have tide tables. We use them to convert them to relative elevation relative to I always forget what time period, that's 30 years or 40 years, kind of lowest water level over the last 40 years, something. So relative to that. So we have the relative elevation and convert that to inundation time.
Yes.
Tide tables.
Okay, so you still use relative elevation as a base. Okay.
There's of course the method is of course it's not incredibly precise and there's some error, but my approach is I rather have a lot of points with some error associated and very few points which are extremely precise, but say,
Yeah. And it's tough to do elevation surveys. Yeah,
yes.
I mean, I was doing it in Mandai Mangrove and I had.
Oh, you did with Dan Fries and Ted Webb?
Oh no, we just did it. I'm under Kyle now in NTU and we just did it like just a week ago. It was tough doing elevation profile of the Mandai Mangrove, so I understand.
Yeah, it's very, very.
The pain.
So just if if we look at this in a more restoration like point of view perspective, I was just wondering, so this is study compared with a Indian, so like on Bonnier, there's just three mangrove species, so it's quite like, easier compared to this. But you've been talking about inundation time period, light, shade. What about what's in the soil? Because like for example, on Bonnier, the major driver for like why the restoration plan were not working, because the first thing that you feel when you go into the mangrove forest is the rotten egg smell, right? So this hydrogen sulfide, and that's related to the bacterial communities. And basically, we found that these different species, so red mangroves and black mangroves, they have substantially different microbial communities inside the rhizospheres. And because of that, black mangroves, which basically live on the like not so close to the land interface, but more inland, well, they could, but the red mangroves, which are need this like higher water elevation to survive, they had microbial communities that was much more it was much more of some species of bacteria which couldn't stand these high hydrogen sulfide levels. So I think, especially in the case of like abandoned fish ponds or like degraded areas where restoration is not working, maybe it's also because of something there's like in the soil. So I bet you think of your species distribution.
Well, yeah, I'm convinced there are many other variables that are playing a role. Also, that to start, Pulau Ubin is relatively uniform. If you would have done at a similar kind of island to the southern part, like Sandy or whatever, then I would be very curious what to see that. But unfortunately, we don't have that contrast in Singapore. But that's partly what I said. So we have one. Pulau Ubin is very small and relatively uniform, I would say, soil-wise, it seems. That's why I really would like to repeat those studies. First of all, there are different degrees or scales at which those variables matter. Also, if you have major difference in soil types or major difference in where you are in estuaries, so salinity gradient, etc., those patterns might very well differ. Within that, and then what you're basically mentioning is even a smaller scale, not like within those. You have your major drivers, salinity gradient, etc. Within that, you have locally or landscape level, you have your inundation or your microtopography. And then within that, you would probably have a more subtle kind of ecological species interaction, basically what you're mentioning, bacteria-plant interaction. Well, for me, it's a bit, my view of the literature on mangrove ecology versus, let's say, terrestrial tropical forest ecology is that there's actually relatively more focus on those very detailed processes in mangroves, probably because of fewer species, and because most of the studies are in the north, etc., you have Yale-NUS. And not as much on community ecology. So although I think the most interesting thing is understanding processes, etc., I think we don't even have a good idea of the major patterns. So I think it would be interesting on itself to look at those very detailed processes. But I think it's very difficult to let's say, to integrate them in a larger model if you don't even have an idea how much they vary at larger scales. For me, it's a bit like, let's do this. Let's repeat that across landscape. And when we have a bit of an idea, then we can actually really start designing those more detailed studies. To be sure that we actually get something out of it which is relevant within the larger picture. It would be very interesting. Yeah.
Well, thank you very much, Michiel. And I think there's an opportunity for more conversation at the end as well. So join me and thank you, Michiel. So I'm pleased to introduce our final speaker today, Dr. Marvin Monfreo, who's an associate professor in the Environmental Studies program at Yale-NUS College, but soon to join the Department of Sociology and Anthropology. Associate Professor Monfreo's scholarship lies at the intersection of food and sustainability, with a particular focus on Southeast Asia. Associate Professor Monfreo's research reveals the precarity of marginalized coastal populations who bear a significant share of the impacts of climate change, marine ecosystem collapse, and market failures. His work is crucial in understanding how extreme weather and other stresses bring about livelihood disruptions and impact food security, resulting in smallholder fishers taking greater risks in their hope of escaping poverty. By examining these dynamics, Dr. Montefreio's research provides valuable perspectives for policymakers and practitioners working to address the vulnerabilities of marginalised populations. So please join me in welcoming Dr. Marvin Montefreio as he explores the relationships between climate precarity, food security, and livelihoods in his talk, Surprises, Coastal Precarity, and Food Insecurity in the Age of Polycrisis. Case in the Philippines.
Thank you. Thank you for that introduction. It's a pleasure to be here. My talk is going to be a bit of a shift. I really appreciated the science part. I learned a lot from it. We're going to shift a bit more on the social sciencey side, I think, slightly deeper into the anthropological narratives. I'm an agrarian scholar by training, but I've done so much work, so many stuff on the terrestrial side. So I guess following the trend of talking about what's lacking in terms of data, right? It's actually quite remarkable that there's not enough anthropological or ethnographies of coastal communities, even in places like the Philippines, which is an archipelago of more than 7,000 islands, right? It's just a remarkable dearth of studies there. So that's the reason why I decided to move to studying coastal communities. So what I'm going to talk about today is a snippet of a book project, which is now provisionally titled Gambling Coastal Lives. And you will learn later on why I included the word gambling there. Right? It has to do with notions of as I put here, surprises and this idea of precarity as well. All right. So I'm following an anthropological tradition. We usually read scripts when we present. Okay? So allow me to share an excerpt from my field notes. In the morning of November 7, 2013, in Capiz Province, Kuya John Ray was ready to dry dock his fishing boat in response to the orders of the town council in anticipation of the arrival of Typhoon Haiyan. Used to dealing with typhoons, Kuya John Ray quickly obliged, asking the help of his neighbors to park his boat some 20 meters away from the beach line near a huge coconut tree. I even tied my boat to the coconut tree just for added security, he said. The following morning, Kuya John Ray woke up regretting to dry dock his boat early, as the sky was still clear. Too bad I could have gone fishing at sea still, he said. A few hours later, the skies turned dark, like night, and the winds were lifting the waves like they had never seen before. In a flash, he and his family found themselves waving in the waters chest deep. They found refuge in a nearby 2-story house, one of the few concrete houses in their community, and stayed on the second floor along with 50 or more of his neighbors. They all watched their bamboo houses and boats torn into pieces and swallowed by the raging sea. It was so sudden, Kuya John Ray recalled. When he saw rubble that was left of their community with nothing left of their house, boat, and fishing gears, he wondered if they could ever recover. The aftermath of Typhoon Haiyan, one of the deadliest typhoons ever recorded in Philippine history, had left an indelible mark on Filipinos. Kuya John Ray's experience of Typhoon Yolanda or Typhoon Haiyan was one of surprise, in spite of the fact that Filipinos in general are used to tropical cyclones. The Philippines is a hotspot for tropical cyclones, with an average of about 20 typhoons entering the archipelago's boundaries and 10 making landfall every year. While the frequent onslaught of typhoons may have made Filipino coastal dwellers familiar with these environmental events, learning to prepare for and recover after each typhoon, occasionally they seem to be taken by surprise. For Malte Faber, Rayner and Manstetten, and John Krups, surprise is a confluence of risks and uncertainties. Drawing from philosophy of knowledge, they theorize an anatomy of surprise that distinguishes risk from uncertainties. An event is a manifestation of risk if the outcomes are known and the probabilities of those outcomes happening are known as well. The Filipino fisher folk, for example, may know the risk of going out to the sea in the middle of a typhoon. The probability of the boat capsizing is high. If the outcome is known, but the probability of that outcome happening is not, then that is called uncertainty. Filipino coastal dwellers now know that super typhoons like Haiyan can happen, but the probability of that happening again in the near future is unknown. There are climate models that attempt to uncover the probabilities, but in most cases, if not all, these models fail to predict. Finally, Faber, Manstatten, and Proops extend our understanding of surprise by introducing the concept of ignorance. That is when both outcomes and probabilities are unknown. We don't know the novel surprises climate change will bring into the future, making it entirely difficult to imagine, let alone predict, with any form of knowledge, scientific or extra-scientific, at our disposal. Studies on risks and uncertainties from a sociological and anthropological perspective are well established, with perhaps the former being more prominent than the latter. For example, risk scholars have determined or have examined the structuring of risk mitigating institutions and enterprises, such as insurance and financial instruments. Many scholars have also studied the emergence of risk-taking behaviors in an increasingly risk-dominated society. In this project, I examine what I call surprise assemblages, which are social material relations that negotiate, co-constitute, and embody risks, uncertainties, and ignorances. In examining surprise assemblages, I also situate how risk, uncertainties, and ignorances interface with precarity, especially debt and food insecurity. I examined the surprise assemblages and precarity in the coastal communities of Capiz, a province on the Panay Island of Western Visayas, the Philippines. Typhoon Haiyan heavily hit Capiz in 2013, and several more destructive super typhoons in the last 10 years. Capiz is also of interest because of the rich marine and coastal resources, which unfortunately are now under threat due to illegal fishing and overfishing. The capital city of Capiz, Rojas City, is known as the country's seafood capital. Seafood produced, such as dried fish, wild and farm sea fish, giant prawns, blue crabs, mussels, and oysters, are typically exported to the neighboring cities of Panay Island, Metro Manila, and even other countries such as Taiwan, Singapore, and Japan. And I wouldn't be surprised if the canned crab meat that you consume here in Singapore actually came from Capiz. The prosperous seafood commodity industry of Capiz, however, has yet to translate to the welfare of Capiznons on the ground. The small fisher folk in the coastal communities continue to live in precarity and poverty, negotiating eroding fish stocks, declining incomes, and rising debt. It is in the context that I examine surprise assemblages, risk-taking, and precarity in coastal Philippines. Today, I will be focusing on a part of surprise assemblages in Capiz that examine fishing structures, in particular, arong fishing. So let me tell a brief story first of a couple who is engaged in arong fishing. 3 months after giving birth, Ate Jocelyn decided to join her husband, Kuya Alan, on his nightly arong expedition. She hopped on the boat carrying her 3-month-old son wrapped around a cloth carrier. The journey to the arong took about 40 minutes on what at that time looked like calm waters. Ate Jocelyn and her infant stayed in the resting hut, where she cooked dinner and nursed her baby, while Kuya Alan was busy manning the arong harvest. I don't know if you see it here, but each arong, right, so it's perched on top of the water. So these are bamboo structures, and there's usually a hut. And then in the hut is where they stay because they would have to do fishing overnight. So close to midnight, the Habaga trade winds kicked in and the waves began to escalate, fiercely rocking the arong. Worried that the waves would knock down the arong, Kuya Alan hurriedly ushered Ate Jocelyn and her baby to the boat. As they were climbing down the bamboo structure, Kuya Alan slipped and fell into the raging sea. Ate Jocelyn held tightly on the bamboo pole while clasping onto her 3-month-old baby. She leapt into the boat, while Kuya Alan quickly untied the rope that held their boat to the arong. As soon as they left safely got into the boat, they watched their arong swept away by the waves and swallowed by the sea. So arong is a spider-like fishing structure made of bamboo built on shallow and deep waters to catch fish at night. They are installed with LED bulbs powered by a gasoline generator, which concentrate light on one spot to lure fish towards the center of the huge net. It's functioning like it's replicating the moon essentially, right? So you can't do arong in full moon, for example. So it's most effective. These nets are then pulled by 3 men several times at night to harvest various kinds of fish, typically anchovies, and if lucky, honeyfish and slipmouth. Arong fishing is a calculated risk where fishers have a sense of probabilities of infrastructural success based on trade wind patterns. Fishers typically put up arong as early as March when the amihan, the cool northern trade winds that bring rough waters from November to March, subsides. Bolder fishers begin constructing arong as early as February, braving the rough amihan waters. This allows them to reap the benefits of arong by an extra month, increasing their chances of recouping their investments. Once an arong is constructed, it stays up until habagat starts. That is when the warm trade winds bring the southern or the southwest monsoons from June to October. Fishers maximize their arong until the bamboo infrastructure naturally gives strong winds, waves, currents of the habagat winds. And this is a photo that I took sometime in October of an arong that is about to give way, right? Naturally, so they expect this. For many of them, they would treat this as a calculated risk, right? But more and more fishers have built arong far out into the open sea, where these structures would have to be pegged to the seabed at a depth of at least 20 meters. Not only are these deep water arongs financially riskier, as these would require more materials and labor to construct, but they are also subject to greater uncertainties. Further out at sea, these infrastructures are more susceptible to the forces of the trade winds and the greater uncertainties of climate change. Southeast monsoons, for example, have become stronger, while typhoons more powerful and frequent. Meanwhile, mature bamboos with thicker and stronger girth are much harder to source and have become expensive, forcing arong builders to rely on younger bamboos, leading to the overharvesting of bamboo groves in the province. So this is a photo. This is actually my daughter here. At night, you would actually see, they're quite far away. You know, at night, you would see them fade away. So these are the arong structures actually. Right? It takes about 40 minutes to an hour to get there by pump boat. So that's how far out they are. So standing on weaker materials and exposed to the harsher elements of the deep waters, arong infrastructures these days are easily damaged and destroyed, and with many not even lasting the early onsets of the habagat trade winds. As Ate Jocelyn, a fisher from the municipality of Ibisan, said, before, even with low pressure area or signal number 1, so we rate typhoons in terms of strength, right? Signal number 3 is already considered high. Typhoon Haiyan, the one that I talked about earlier, was signal number 5, right? So here they're saying that even with signal number 1, low pressure area is even milder than signal number 1. Arongs can still stand. These days, they can't even stand low pressure area anymore. Yet many continue to engage in arong fishing. Part of the reason for their persistence is anchovies, fish that when dried fetch a good price in markets in Rojas City and metropolitan Manila. Popularly known in Manila as dilis, a kilogram of dried anchovies can cost as much as $20 to $25. Another is ponyfish or slipmouth, which when caught in larger sizes and sold fresh can fetch even higher prices. Given the vulnerability of arongs and the promise of high returns, I refer to arongs as risk-taking infrastructures. That is, social material embodiments of risk-taking that manifest everyday languages and practices of gambling logics. As one arong fisher, Kuya Robert from Capi, said, if you put up an arong, it gets destroyed, you're unlucky. If it doesn't get destroyed, you're lucky. Kuya Robert's comment was said in the context of our storytelling about the fisher who lost his arong to a low pressure area just a few weeks after it was constructed. Just imagine that, right? So it took, you put a lot of investment on it only to be destroyed after a week or two. I heard of many other countless stories of premature arong failures lasting only a few weeks instead of the expected 5 to 7 months of lifespan. Fishers commonly use the words malas, right, or unlucky, and suerte, lucky, in describing not just arong, but their other coastal livelihoods as well. Metaphors and similes of risk-taking in the form of gambling become even more apparent when arong is talked about in terms of monetary returns and losses. Ate Jocelyn described arong this way, and I quote, there's a mix of catch in arong. If you catch plenty of anchovies, you hit the jackpot. Sometimes you can earn 3,000 pesos, around $50 in a night. Sometimes 10,000 pesos, that's around $175. If 10,000 pesos, you hit the jackpot. And I did not even have to translate the word jackpot, so they really used the word jackpot. It's like roulette, like the roulette in casinos. Your luck depends on where the ball lands. The catch is difficult, just a matter of luck. 10,000 pesos, even 3,000 pesos is high, given the average earning of a fisher in Capiz is around just about 500 pesos a day. Enabling risk-taking behaviors are credit and debt. Credit and debt play a central role in my research. Whenever I interview a fisher or wrote my ethnographic field notes, credit and debt figure prominently in the everyday struggles of coastal dwellers. It was rare for me to encounter somebody who did not have debt or service. Most of the fisher folk I talked to, such as the women in this photo, who have assembled outside and are waiting to actually do their debt servicing, right? So this is microfinance. They were waiting for the microfinance collectors to come collect their debt. So they had most of them had loans from 1 or 2 microfinance institutions with debts ranging from 10 to 50,000 pesos, interest rates hovering around 10%, and payments scheduled every week. Credit and debt are essential in risk-taking infrastructures. Arong requires large capital depending on the risk tolerance of fishers. If they wish to erect the arong far out at sea, then the investment would be higher, ranging between 150,000 to 250,000 pesos, or roughly about 2,500 to 4,300 US dollars in today's exchange rate. That's a fortune for a Capisnon fisherfolk. Such an investment can only be enabled by remittances and credit from formal lending institutions. The motivation to engage in risky livelihoods is driven by the aspiration to achieve economic mobility. When fortunes align, windfall profits provide precarious fisherfolk a boost in economic relief, which they reinvest in education, migration, and or additional livelihood assets, such as another boat or another arong. Each reinvestment has corresponding implications on surprise mitigation reverberating throughout the assemblage. Greater risk-taking comes with the promise of higher returns that offer the prospect of pulling fisherfolk out of poverty. Arong owners who have benefited from the windfall profits and upgraded their homes to concrete houses serve as inspiration to many others, for example. But what happens if fortune is not on one side? Imagine if an arong fails prematurely. Such failures portray the high-stakes nature of the gamble. Even when they are strategically built during the time of the year when the sea is calmer, a fisher may find its investment crashing in the sea due to an unexpected off-season low pressure or storm, even just days or a few weeks after it was erected. Hopes of winning the gamble then quickly turn into anxieties of debt, with some giving up the dream entirely, while others betting in the red and miring themselves in debt traps. When luck is not on their side and debt servicing becomes a priority, which is almost the norm, food is one of the first to be compromised. Over time, risk-taking and debt have forced Capisnon fisherfolk to gamble on their own health as well. Increasingly, indebted fishers compromise on the quantity of meals they consume, and most prominently, the quality of food. For example, they have increasingly relied on processed foods, such as canned goods and instant noodles, available in neighborhood micro-enterprises that allow selling foodstuff on credit. So this is the meal that I shared with my host family, who had just, when I arrived, just told the story of how their arong collapsed, right, prematurely. And at that time, I mean, dried fish is a staple for them. But then this time they were eating a lot of instant noodles, essentially, and the instant noodles were coming from the micro enterprises that provide credit. So meaning that, oh, they can get food, but it's on credit as well, right? And a lot of this food stuff that are sold in these micro enterprises are your low quality, high sodium processed food. So let me conclude here. My conversation with Kapisnan Fisher folks whose fate was not brushed with luck were replete with narratives of despair and regret. So while luck and windfall profits can be emancipatory, in the end, one's fate lies on the whims of chances. Left to their own devices, smallholder fishers negotiate surprises with a modest sense of control, shaping their material world as best as they can to improve their own lives. Often, they are resigned to just the luck of the draw. Thank you very much, and over to you.
And for sharing the stories and the stories of the people that you take in time. Questions?
Are fishing stocks declining because of external large fishing fleets from China and other places, or locally also?
It's mostly because of trawling. Some are encroaching from China, but these days, because of the geopolitics, right? So they're more of that guarding of the borders near South China Sea / Western Philippine Sea. But there's a lot of local trawlers as well. That's one of the things that they're able to patrol. Really, yeah. So many of the local fishers would put the blame, of course, on the trawlers. And the problem is not just reefs being destroyed by the trawling fishing, but it's also a lot of them would have these various forms of fishing livelihoods around the coral reefs, right? They would have these floating fishing structures, Arong being one of them, but there are others as well. And if a trawler comes, it destroys their nets as well. So it's not just the reefs, but the nets. And the nets constitute about 30% of their fishing livelihood in terms of investments. Yeah, so a lot of them end up, so for example, they lay the nets out there at night, then they come back the following morning to collect the fish. When they arrive there, the nets are already ruined because of trawl fishing. So yeah, so that's when they start borrowing a lot of money.
The fish deeper, further in the sea, is that more reliable or more abundant?
It's supposed to be more abundant, right? So it's extremes actually. So when you go out there, there's the promise of right? So if you are lucky, you can actually win a lot, right? It's like gambling in that sense, right? That some of them can even recoup their investments within just a week, for instance, right? But in most cases, most of the stories that I hear, it's really losing the bet in that sense. But they still somewhat kind of hold on to that promise that, oh, we will win that jackpot, right? Yeah, if we get larger, bigger fish, for example, more high value types of fish that are available out at sea. But it's the reason why they go out further out to sea is because there's nothing much left to catch near the coast. So they're taking more of that risk.
At the front.
I was recently in Bintan Island on a field trip, and they have something similar. It's called a kelong, but
Yeah.
they are actually mounted on swimming devices. So it's a very similar construction, but they pull those things out and they anchor them. They fish and then they come back, so they can kind of like calculate their risk better, I guess, because when they see the storm coming, they just bring those kelongs to the shore and protect them. Why would these differences like exist? Why would, since it's the same region, more or less, Southeast Asia, why would they go and construct in a depth of 20 meters, which is crazy also in terms of like manpower, because they have to dive there, when they could actually just make those things floating?
So again, depends on how far you are from the coast. So there are versions of kelongs in this community as well.
Oh, really?
There's probably close to about 20 different kinds of fishing livelihoods. Yeah. More than half of which are structure based, right? They would have to build these bamboo structures to get fish. And some of them are building like huge traps, for example. You have kelongs, floating platforms where they grow, for example, they farm fish in that sense, right? But they farm fish out in the sea rather than in ponds. People find that less of a risk, right? But it's a different risk profile in that sense. Because for that one, they would have to invest longer term. So I did not talk about that because it's an entire story. That's actually a chapter in my book just about that. Where they would have to have discipline, financial disciplining to reserve a part of their everyday earnings to feed the fish in the kelongs, right? And sometimes it would go as high as like 50% of their earnings per day, with the promise that they would be growing these high value crops in their kelongs, right? Not crops, high value fish in their kelongs, right? Which they will harvest by the end of the year. So some people gravitate towards that because they feel that they have a lot more control of the risks associated with that form of fishing. But there have been issues in the past as well of how surprises caught them, how certain circumstances caught them by surprise. So the host where I stayed, for example, also has a version of a kelong. And they have been investing on it for close to about 10 months already. So they were 2 months far away from reaping the benefits, right? So imagine I would see them every day waking up and fish, and then taking a part of the fish that they get, chop them up and feed it to the fish, the high value fish in the kelong, right? And that constitutes about 50% of their earnings every day. They would do it every single day. And when I arrived there, apart from their arong being destroyed, a few weeks back, their kelong was, all the fish in their kelong died because there's a fish pond that released their waters. And then the fish pond had it's a overload of nutrients, right? So essentially killed the fish in the kelong. So it's 10 months of investment time. It's like that. So now there's a lot of, so people are now kind of reconsidering, are kelongs, there less risk in kelongs as compared to arong. So it's an interesting, so one of the things that I'm studying is how they make decisions, right? And what informs them, how do they make these calculations in their heads, for example.
That diagram you had, surprise assembly, is that referring to these relationships?
Yes, the different relationships,
Yeah.
right? And how, for example, when you try to alleviate risk in one particular fish livelihood, whether I'm looking at whether that alleviates risk in others or actually creates risk in others in other parts of their livelihood networks as well. And that includes like migration. So some members of the family, for example, migrate and work in fishing vessels abroad that have really terrible labor conditions, right? And so that's another form of risk taking, right? So they would go there, be gone for a year, and then take all the risk, right? There's actually a higher chance of getting injured or dying in commercial fishing vessels than being at home, for example. But then they would do that so that they would get huge amounts of resources, remittances that they would then use to invest in fishing structures back home, like in arong or in kelongs or whatnot, right? So so what I'm looking at is the flows of these risk mitigations, essentially, from one area to one.
I think if we can maybe just take the time, I think, to bring things together. There is actually a question online that perhaps Marvin, perhaps we can maybe have time to answer after the closing remarks.
I'll do that.
If that's okay, and then have a conversation. So thank you so much for sharing and talking about the like to invite Associate Professor Lee to close, but certainly we'll be engaged online as well.
Thank you so much for staying here the entire time. I approached this with a lot of fascination. I'm not an earth scientist or an anthropologist by any means. I am a linguist, but I look at linguistic diversity and the threats faced by that kind of diversity. So it's kind of interesting for me, the way different people are talking about climate change and risk in different sorts of ways. And we covered quite a lot of ground here. We look at advanced 3D methods of Earth monitoring and considered how these might have repercussions for policy making. We also heard from an earth science perspective how coral reefs are under threat and how this might have other kinds of repercussions on services that coral reefs provide. Then we turned to the distribution of mangroves, considered how that data should most probably inform restoration projects. And then we also importantly considered the human experience in looking at these Arong setups in the Philippines and the relationship between coastal precarity as well as food insecurity. So it's clear that this sort of work should have policy impact, and we know we'll invite you to consider these links further. But that being said, I'm fully aware that dinner is outside, it's waiting. So we'd like to thank all our speakers and our moderator, Dr. Owen, and as well as our organizing staff for the event, and please have dinner. Thank you so much.